Once we have, in the last chapter, we have talked about mobile ad hoc networks. Now we will consider a new type of network and then analyze it. So this is known as downlink cellular network, and I will spend some time in discussing why this is different than MANET and why it is called cellular network, and then we will see what kind of changes we have to do in order to analyze such systems. So in the MANETs we discussed in the previous chapter, this TX-RS pairing is prefixed, right? So this means that it is possible that one of or more interfering transmitters can be closer in from the receiver in comparison to its own paired transmitter, right? So look at this is a typical receiver, and right, and its pair is this one. It is transmitting, but since the pairing is fixed, there can be other pairs all across, and it may happen that the other pair transmitter is actually closer to this receiver than its own pair transmitter. And we cannot avoid it because all of these pairs are independent and this pairing is already fixed. So in this case, the power received by the interfering from this interfering transmitters can be more than power from the desired transmitter, and thus the assigner can be below 0 dB in this case. So such kind of implementation works when you have a sparse network, right? When the transmitters are far away, so there is very less likely that you will find another transmitter close by. Okay. But as we go to large networks or dense networks where there is a high density of transmitters, this probability that you get another transmitter will increase, right? Moreover, if you yeah, so to provide a reliable service in this case, provider need to guarantee that a signal power must be less than the interference power, right? At least most of the time. So this requires dynamic pairing such that the desired transmitter is always effectively closer to a receiver than other transmitters. So you cannot fix the pair, but you will decide the serving base station on the go, the uh, based on the scenario, right? And as the users move, this pairing may change, right? You may find that there's a new transmitter which is close by, and you want to switch to that new transmitter. So there is a mobility aspect is also there. Okay, so one of this example is known as a cellular network. So there we have here we have a concept of cells, what means that a cellular network consists of many transmitters, right, deployed at different locations to cover a region, right? It's not just a small region, a very big region like a city. So you deploy the base station at many places, which can be intelligently calculated. These transmitters are known as base stations, and all base stations are connected to each other via a infrastructure backhaul link, right? So if this transmitter wants to talk to this transmitter base station, then they can communicate via this infrastructure backhaul links. Okay, and then there is a lot of other equipments here which route the packets and do billing and other things. So this backhaul connection is generally wired and is a high-speed optical fiber cable connection. Okay. Sometimes you may also see satellite connections which can connect to base stations. The users are either known as users or mobile users, owing to their mobility. Right, those users can move into different places and can connect to different base stations. Right. So what happens is at any point of time, the user is connected to one base station. Okay, and so suppose there is one user connected to this base station, and one user connected to this base station. And suppose this user wants to talk to this user, then what it does it transmits its data to this base station. Base station will send this data to this base station via the infrastructure link, which will be received by the user from this base station. So that is how a typical connection will look like in a cellular network. Okay. Now, how does the user decide which base station to connect to, right? So that basically there are different criterias on which you can divide the space, right? And then you will say that so the complete region will be partitioned to small regions, one region associated with one base station. And if the users fall in a particular region, it has to connect to the base station associated with that region. Okay, so these regions are known as cells or association regions or the coverage cells, and the user will just find out in which cell it falls, and then it will connect to that base station. Okay, and these cells are predefined based on some criteria. And that is how the name cellular network is coming up, because this network is made from multiple cells. A network which partitions the complete space into disjoint cells, each associated with one base station, is termed cellular network. And the partitioning is done in a way to ensure that the user gets the base station that gives the best coverage possible. Right. Now, this best is in quotes because it's not always clear what is the best thing, because there are different aspects. For example, do you want the highest rate? Do you want the highest coverage? Do you want the highest reliability? So there are different factors, right? So based on our interpretation of best, you will have different criterias on which you want to uh, divide or partition the region. Okay, and one simplest example is to select the closest base station, right? So you just, if the user is here, it find a distance from all the base stations and find which is the base station which is closest, and the user will connect to that base station. Okay, so the all the points, all the location for which this user is the closest, they will make the cell of this base station. Right. Now, if a user changes location and come close to another base station, the connection will be switched to a new base station to facilitate the desired signal is more than the interference now. This such kind of switching is known as handovers. And the partitioning into cells can be done in many ways, right? They can be static based on geometry or can be dynamic also, right? So many times you will see there is a fading. So because of the fading, the channel may keep on switching, or there is a dynamic blockage that some vehicle came into the in between. So the base station is no longer can provide you a direct line of sight. So you may switch to one base station which is giving you better signal. Right. So we'll talk about some of these criteria just to understand it better. Let us first remove fading and interference from other base station. Right. Let's just assume that the network is sparse, so you don't see that much interference from other base stations, right? So if we fix the threshold, uh, so we are ignoring fading and interference, so everything is geometry based. If we fix the threshold for successful transmission, each base station will have a circular area with radius that is equal to the maximum distance at which the base station can provide SNR above the threshold, right? So when you leave the fading and interference, then if we just focus on the SNR, right? So SNR is what? Signal power divided by the noise, right? And signal power decreases with the distance. So they would be, so if I fix that I want 10 dB of threshold of SNR for successful transmission, you will see that there is a distance after which the signal power would be lower than 10 times the noise. So the SNR will be less than 10. But before that, inside that distance, the SNR would be more than 10 dB. So for every base station, there will be a region around it. There will be a feedback some distance in which the cells can provide you the enough SNR coverage. Okay, so if you look at this figure, suppose this is the distance at which it can provide you 20 dB. This is the distance at which it can provide 10 dB. So if I require 10 dB, then I can only connect users up to this distance to this base station. Beyond that, if there is no other base station, the user will not get enough coverage. right? Or if they have another base station in that. So for example, if you look at here, this is outside 10 dB, but it may be inside 10 dB range of this base station. So it will just connect to this base station. Right. So let us see one example. Suppose a noise limited network, so interference I'm ignoring. A base station can transmit successfully if the SNR is above 10 dB. So if I assume transmit power 1 watt and the noise is minus 80, and assume power law path loss with near field gain minus 40 dB and the exponent alpha. Okay, so the maximum distance r at which the base station can transmit without, uh, transmit successfully is given by, uh, so suppose it r, then the signal power would be PTCR minus alpha and noise will be sigma n square. That should be more than 10. So if I put the value of transmit power to be 1, C to be 10 to the minus 4, which is minus 40 dB, R to the power minus alpha, and the noise is 2 to the power minus 8, then I can find out that R should be less than 10 to the power 3 by alpha meters. Okay, so if alpha is 2, this will be 10 root 10 meters, right, which is approximately 32 meters. So then you can say that at 32 meters, around each base station, all the cells can get enough SNR. Okay, so in some sense, you can also say that if there's a base station attacks, any user falling in a ball around this base station at R radius can get enough SNR if it connects to this base station. Okay, and outside that, it will not get coverage. So this region around the base station is known as the SNR coverage region of the base station. Okay, and if SNR is the only criteria, then this will be the association area also. Right. Now, when we are assuming sparsity, we are assuming that the base station are very far away, so that this SNR regions do not overlap with each other. Okay, so suppose it is 30 meters. Suppose this means that other base station are generally more than 60 meters away, so that if you look at the two SNR coverage region, they are not going to interfere. So there is no confusion on which base stations you want to connect to. Okay, so these coverage regions are static. If a user falls in one of these regions, it can transmit receive its data. And in a noise limited case, when the base station is sparsely located, these circular regions area do not intersect each other. Right? This means all location will only receive decent signal coverage from one base station, maximum one base station, and there will be no interference. The association of user to base station is easy here because the user fall in the coverage region of only one base station. Right? They are outside other base station regions, so they cannot connect to it. So it is very clear which they want to connect to. Right? So they will connect to the base station whose coverage region they fall in. Right? So the complete region is divided into these small circles. Right? And all the region where there is which do not fall in the circle or coverage region of any base station, they will be coverage holes, right? They will be outage there. And if the users falling in those regions will not get coverage from any base stations. Right. So what happens if this coverage holes are a lot, then the provider would like to either put more base stations or increase the transmit power, right? When you increase the transmit power, the coverage region will increase. Or you can have more base station to cover more regions, right? So to reduce the coverage holes and provide coverage to all users, base station density in a cellular network must be enough such that the base station SNR cells cover whole region, right? Now you will find out when you try to do that, when you try to make that SNR regions are covering the whole region and they are circles, right? So this means to include all the area, these circles need to intersect each other, right? So you can look at this figure. If you have very small region, if they are not intersecting, then they will have very large regions where there is outage. Now you want to increase it. If you go to up to this limit, these regions are touching each other, but then there is a still coverage hole. If you want to cover that, you have to further increase the coverage area, and thus eventually the all points will be covered, but there will be multiple locations which are covered by multiple base stations. So this means that the base station cells will intersect each other. Now, intersection of coverage area means that these locations inside the intersection, there are more than one base station which is providing the descent signal, right? More than 10 dB signal. So the interference is now significant and cannot be ignored. So a location which is equidistant from both base station, right? It will be, and it is in coverage area of both base station, will receive the same power from the base station. Hence, the SIR from any of the two base station would be below 0 dB. So the SNR at this location may be above 10 dB as it falls in the SNR coverage region of both, but the SINR total can be less than 0 dB. So even if a user is in the SNR coverage region of many base stations, its received SINR may be lower than that of the required SINR from one or all base stations, right? So if it's not equidistant, but it is falling in the coverage region of 2, then it may happen that one base station, from one base station, it is getting signal power more than suppose 20 dB, and from the other base station it is getting just like 10 dB. So the ratio can still be more. So the question is, when the user is associated, so in this the user is falling into the SNR coverage region of 2 base station or more base station. So in that case, it can only be connected to one base station. So which base station it should connect to? Right. So if it fall into the coverage regions of more base stations, more than one base station, which base station it should connect to? So the question arises, which base station we should select, and the problem can be formally stated in the following way. How do we partition the space into association cells such that users falling in the cell of the best base station for it, out of all base station in whose SNR coverage region it is falling in? Okay, so if the users are falling into multiple coverage regions, which base station I should connect to, right? And once I do that, what will be the how does this association cell will look like, right? So once you have decided that this location would connect to this base station, you are basically defining the association cells of all base stations, right? So they are both same thing. Either you just tell a user should connect to which base station, right? In that way, you are basically telling that this location, if the user is, we should connect to this base station. So you are basically defining the association cell of each base station, which just means that you are partitioning the space into association cells. Okay. So a law which determines that is known as association law. A law which defines the association of each user location Y to a base station B. So BY is the base station of the user at Y. Given the set of base station phi is known as the association law, or the association criteria, or a selection rule. There are multiple names for it. So you need to know where the base stations are. Given that there is a law which will map the user location to the base station index, that this base will connect to this base station, right? And it just depend on the user location. So once if there are two users at the same location, they should connect to the same base station according to this law. So this association law will dictate what locations are associated to a particular base station. It will also determine the partitioning of the space into cells, right? So once you have said that these many locations are mapped to this, what you do is you collect all. Once you have decided that this location will map to this base station, you pick one base station and you find all the points which will map to this base station, right? So all this point will make the association cell of this base station. Then you take the base station number 2, find all points which will map to base station number 2. Those points will make the association area of the second base station. So let Cx denote the cell of the base station at X. Then Cx is made from all locations such that they map to the base station at X. Okay, so you pick one base station at X, and the coverage region would made from all locations which are mapping, which are associated with this base station. Okay, so now let's talk about some standard association laws which are mostly commonly used. So we will consider a set phi containing location of all base stations. We consider a typical user at location y, and we will discuss different association rules which define rule for selecting the base station for this user out of all base station in phi. Okay, let's talk about first the networks with no fading. So they are more deterministic. So in this case, we first talk about the highest receive power base association. So recall that the receive power from a base station at xj at the user at y is given as receive power is transmit power into near field gain into the distance, which is xj minus y norm, and that distance to power minus alpha. I'm assuming a standard path loss. So consider the rule where each user is connected to a base station which provide the highest receive power among all base stations, right? So what I do is I calculate this receive power from all base station in phi and find out which one is giving the maximum, right? And since the transmit power in C is constant, this eventually ends up telling which one will give the maximum value of xj minus y norm minus alpha. Right. So what I want to do is for any location y, I want to calculate the argument of this maximization problem, the one xj which will maximize this, and I will connect that y to that base station. So I will associate that the base station as a base station of location y is this. So let us first consider two base station, one at this and here. Now one at x1 and one at x2. And then if you want to, this is a user, the receive power, if the distance is R1 and R2, the receive power here is R1 minus alpha, and from this is R2 minus alpha. And if I want to make sure that if R1 minus alpha is more than R2 minus alpha, then I'll connect to base station 1. And if R2 minus alpha is more than R1 minus alpha, then I'll connect to base station 2. Now receive power is proportional to R minus alpha. So this means this is equivalent of saying that if R1 minus alpha is more than R2 minus alpha means R1 should be less than R2. Right? It is minus power. So if R1 minus alpha, the receive power from base station 1 is more than receive power from base station 2, this means base station 1 is closer. So this is just equivalent of saying that if R1 is less than R2, then connect to base station 1. And if R2 is less than R1, then connect to base station 2. Right? So in other words, I can just say if there are the user at y and the two base station at x1 and x2, this means if x1 minus y, the distance of y from x1 is less than the distance from the x2, then connect to base station 1. Otherwise, connect to the base station 2. So this law is basically just saying that you want to connect to the one which is closest to you, right? So for all location y, right, says that x1 minus y is less than x2 minus y, those points for which x1 is closer than x2, that will be associated with x1. So this means the association cell of x1 is made from all the points for which x1 is closer than x2. Right. Similarly, for x2, the association cell will be made from all the points for which x2 is closer than x1. And this partitioning, because if you look at y, either x1 will be closer or x2 will be closer, right? So all points are covered. If x1 is closer, that point will be in the association cell of x1. If x2 is closer, it will be in the association cell of x2. Right? So because all the points are covered, this will create the partition of the space. Right? So first will be the base station 1 region and second will be base station 2 region. Right? So how does this partitioning look like? All points for which base station 1 is as the closest base station will fall in the base station 1 and rest of the point will fall in the base station row. Okay? And the user falling in the base station 1 area will have to connect to the base station 1, while what user fall in base station 2, they will connect to base station 2. right? So how does this area look like, right? If you divide the space into two regions, right? All the points, so these are two base stations, and all the points for which this is the closest, right? They will be in this region, right? So you know that the coverage region of one base station is constructed from all locations that are closer to this base station compared to the other base station, right? So how do we do this division? We can just take a perpendicular bisector, and then we know that all the point location falling in this point region, for them both are equidistant, and all the locations which are falling in this side of the line, for which this will be closer than this, right? So all the location in this region, for them bs1 is closer, so they will make the base station 1 coverage area, and for this side of the uh, uh, region, this side of the line, all the users falling in this area, for them base station 1 2 is the closest one, right? So eventually the partitioning look like this. The gray area will be base station 1, the green area will be base station 2. So these will be the coverage region of uh, two base stations, right? Similarly, how do we extend it to for multiple base stations? So if there are, for 2 point, it was just perpendicular bisector. If there are 3 points, what you can find out that for these 2 points, I can create a perpendicular bisector for, and all the points here, for them this base station is closer than this. Similarly, I can create a bisector here, and for all the points this base station is closer. And then for these 2 points, I can create another bisector here, right? And it says that all the points on this side of it, for them, this base station is closer than this base. Similarly, for 4 points also, you can create these boundaries for each pair and then compute what are the area for which a particular point is the closest one. This can be extended to n or even possibly countably infinite number of points in a set phi. Therefore, given a set of B, for any base station x, the cell of base station x is given by Cx is made from all location y, for which x minus y is less than any other x prime minus y, where x prime is one of the point in phi except x. So this just means that you all the location for which x is the closest point out of all points in phi, uh, those location will make the coverage area of x. Okay, so yeah, basically coverage cell of x is given by all location for which the x is closest of all the points in the set phi. So this kind of partitioning is known as Voronoi tessellation. So this Voronoi tessellation refers to a tessellation or partition of area into n small areas given a set of n center points xi, such that all points lying in a particular area vi is closer to the ith point compared to other points. Okay, let's see some examples of Voronoi tessellation. If you have this 19 cell grid, if you have base station in a particular location, then their Voronoi cell is given as this hexagonal cells. Similarly, if you have base station in the square grid like this at integer point suppose, then the Voronoi tessellation is given in the following format. And if you have a random placement, if you have base station at random location, then their Voronoi tessellation. Okay, in for any point you can just verify that. Suppose this is the Voronoi cell, so any location in this cell, if you calculate the distance of all points, the distance to this point will be the closest one. Okay. Either way to compute the Voronoi is you can put a ball of radius 0 at each point, and then you let the balls grow with the same speed. Okay, and each pixel at any point at any time instant, each pixel is assigned to the point whose ball touches the pixel the first. Okay, and once the ball has touched, then you just assign that color to it. Okay, so they are going at the same speed, and for every pixel, you just find out which ball touches this point first, pixel first, and you assign to that ball or that center. Okay, and once you do this process to infinity, time to infinity, you get the coordinate solution. Okay, or you can just take each point, calculate which point is the closest one, and assign to that. Okay, so that was closest distance or highest receive power based association. Now let us see the other way would be, see, receive power is not the final performance metric, right? We see that receive power can be more, but the assigner can be low. So in ideally, if you want to maximize the coverage, you want to connect to the base station which provide the highest assigner or highest SIR, right? So if there are multiple base stations which are providing decent SNR to a user, you want to choose the base station which provides the highest SNR, right? So if I go by that criteria, we would say that we want to connect each user to the base station providing highest assigner among all, right? And what our claim is that this association is same as maximum power based association when there is no fading, right? So how do we show that? That whether we select the assigner based association or the maximum power based association, we will get the same base station, same association. So for simplicity, let us consider a UE at the origin. We need to find the base station which provide the maximum assigner to this user amongst all base stations. Okay, so the ith base station, from the ith base station, if we select that base station, the assigner from that base station would be equal to the receive power from xi divided by sigma square plus summation of interference from all other points. Okay, so you can see that I have only kept the path loss and I have removed the transmit power and near field gain, transmit power and other factors from this expression because they will just cancel. Okay, so the interference based on will just cancel each other. So now we need to select I that maximizes the assigner. So we calculate assigner from all base station and we compute the argument of this maximization, that I which will maximize this. And we call that I as 0. Okay, so this is just arbitrary ordering. We will order the base station which give me the highest assigner as the 0th base station. Okay, so this means the base station 0 provides the maximum assigner among all base stations. So it's just that we calculate from this, and then for that user, whatever base station is giving me the highest receive power, I call that 0. Okay, so let us consider two case. Let's consider two base station. First at x1 and the other is x2. So power received from first is x1 minus alpha, and I have removed transmit power and near field gain. And power received from base station is x2 minus alpha. So assigner from the first base station, if you select first base station as a serving power, the assigner is given as norm x1 minus alpha divided by norm x2 minus alpha plus sigma square. So second base station will be as a interfere, act as an interfere. First acts as a serving base station. Similarly, for the second base station, if I had selected that as a serving base station, my assigner would be x2 minus alpha divided by x1 minus alpha plus sigma square. I call this assigner 2. And here the first base station is act as an interferer, so that power is in the denominator. So condition that we want to select base station 1 if assigner 1 is more than assigner 2, right? So we want to compute that what are the cases, what are the values of x1 and x2 such that this condition would be true. And we found that we just put the assigner 1 and assigner 2 value. Then we cross multiply. Right? And from this we can deduce that if this condition is equivalent of saying that norm of x1 minus alpha should be more than norm x2 minus alpha. Right? So if this condition is true, then the assigner 1 would be more than assigner 2. Similarly, if assigner 1 is more than assigner 2, then this condition should be true. So they are equivalent condition, and which means that you want to select the first base station if first base station is the closest one, or the first base station gives the highest desired signal power. Okay, so this will the reason if you have two base station, one is closer or one is giving higher power, right? It is best to choose that, because by choosing this, second base station power is less. So once you choose this, you are getting a good power and less interference. If you choose the other base station, then because that base station gives you low power, this will give you low serving power, and the first one which was giving me higher power, that will act as an interferer, which will further reduce the assigner, right? So by choosing the base station providing the highest received signal power, you are making sure that the serving power is high and the interfering power is low. Okay, so just means that this and the highest desired signal power base association are the same association. Okay, in the case of network with more than two base station, we can do comparison for every pair ij, right? And assuming a sigma n square to a summation of power from all base station other than I and j and noise, right? And then we can show that for all pairs, the one which is closest is which we have indexed as 0. The one which is closest will also give you the lowest signal power. Sorry, the highest assigner. Okay, and due to ordinarity of real number, it is always possible to find one base station which wins over all other base station in pairwise comparison, right? And it will be decided by the one which will maximize this particular receive power. Now, if we consider random fading also, and then we can see how it affects the association law. In presence of random fading, association being little tricky, and we have an extra choice, either we want to incorporate fading in the association criteria or not, right? So in the first one is highest instantaneous assigner based association. Remember, instantaneous means when we include the fading into the receive power, we call it the instantaneous assigner. So in this case, instantaneous receive power at a user from the base station at xi is given as this one. So there is an extra factor fading hi here, which is a random channel coefficient, which value can be very small or large depending on the instantaneous environment. And the selection criteria would be you want to select the one which will give you the maximum instantaneous service power, right? And I've again removed PTSCI, assuming it is constant for all base stations. Now, since HI changes over time, once it changes, it may happen that we have to switch the association, right? So earlier in the previous case, when there was no fading, there was, and all the base station location was fixed, right? In that case, there was only one base station which is closest, and you want to select that. But here, fading is also there. It may happen the base station which are far away but have very good fading, that will give you the maximum signal power. So, and then HI would change. So other base station can also give you highest receive power. So, and you want to switch between these two base stations. Okay. So in the case fading is changing very fast, this may not be very practical to switch association in short term duration. Okay, and that is why sometimes people say that we don't want to go for instantaneous single power, because that requires a lot of switching and it may require a large overhead. Instead, we want to get more reliable base station, which provides me the highest receive power on the average. Okay, so in that case, you can notice, suppose the average value of fading is mu h. In that case, the average receive power at a user from the base station at xi will be just averaging of this. These are all constant and only hi is random. So what you get is average receive power is equal to mu h into PTC norm of xi minus c. And because mu h, pt, and c, these are all constant, we can remove that. This will come out equivalently to maximize the, this is equivalent to the association criteria of maximizing the receipt power when there was no fading. And we can show that association maximizing average receipt power is same as the association maximizing average assigner, right? When fading HIs are IIDs, right? So this is equivalent to the association giving the stochastic dominant assigner. We will talk about this in a later lecture. And we have already talked about what Voronoi cells are and what association is. So we directly start with defining a general cell network, and then we will see how we can analyze that. So first we will define a general cell network. So a cell network M consists of the following components. First one is the base station process file, which will define where the base stations are located, and then a user process by user. We do not take any distribution for this user process, but we will assume stationary. And in general, we do not care about all the users. We will take a arbitrary user. And if you recall the definition of typical user, it is, or typical point, it is one point taken arbitrarily from the whole process. So we will take one typical user out of the whole user process and calculate the do the analysis for that user. And because it's stationary process, so we can take that user at the origin. Second thing we are going to talk about is general receipt power level function. So we will call it PRX level, where X denotes the location of the base station. Okay, so this denotes the power of any base station located at X, and it denotes its receipt power at the user, which is at the origin. So it is a function of X. Okay, so we can take it as a instantaneous power or average power, but we have to remember this thing, that association law, the law which will decide which base station is associated with this user, will only depends on this function value. Okay, so if the association depends on the instantaneous power, you make power level function representing the instantaneous power. If the association depends on the average power, you make this function representing the average power. This can also be a random function. It means you can include fading. For example, instantaneous receive power includes fading. It can have any random variable. Okay, but it only depends on the location of X and the variable associated with that X. It doesn't depend on any other base station. Third is, now we will talk about the association law, right? And as I said, association law is a function of the power level value. It does not depend on any other power. So it will be given by a function g, and you apply g function over all base station and check which base station gives the maximum value of g. Okay, so whatever base station gives the maximum value, that will be the serving base station. The user will be associated with that base station. Just for notation purpose, we call the index of that base station as 0. Okay, so this numbering of x1 x2 can be arbitrary. So the base station which we associate with is the 0 index, and the rest base station will be 1 2 3 4. So the base station we associate will be denoted by x0. Okay, and this is arbitrary indexing, just for notation. The fourth thing I'll talk about is the instantaneous receive power function. This is the actual power which is received at the user. Okay, so when I compute SINR or any other performance evaluation, I'm going to use this power, and this again depends on the power level function, but it can include more random variables, or it can consider other factors also. Okay, because so one example is the suppose you take the average power base association, so your power level will be just based on the path loss. Then this function h will include one more fading which is multiplied by the power level, and that will be your instantaneous power. Okay, so with this all properties, the general network function M would be a set of or a collection of phi user, F which is the power level function, G which is the association law, and H function which is the instantaneous receive power. Once I have fixed this, the network will be fixed and the performance can be determined. For this network, the assigner is defined as assigner 0. Why I'm calling assigner 0? Because it is the assigner from the 0th base station. And that is equal to instantaneous receipt power received from x naught divided by the noise sigma n square plus summation over all points except x0. And you sum the instantaneous receive power from each of the base station to calculate this. Okay, so the assigner we just talked about is a random variable because serving power, which is in the numerator, depends on the base station distance, and the base stations are random. Serving power is random. Similarly, interference is random. So the overall assigner is a random variable, which is a function of point process realization. So if we want to talk about the performance of a cellular network, we say it's assigner. An assigner is not a number. So how do we characterize a random variable? We can use CDF or probability distribution function or Laplace transform, something like this. So here we are going to define a metric which we call coverage probability. Okay. So what is coverage? A point is said to be, or user is said to be in coverage when the received power or the assigner, let's say assigner, that user is above some target threshold tau, right? And if you remember that what we discussed in Manet, this tau is depends on your target application also. So if you're going to talk about audio, you may need smaller threshold. If you're going to talk about a video conferencing or YouTube videos, then you need a higher threshold. So coverage probability is the probability that a user is in the coverage, which means the probability that the assigner you get is above that threshold tau. Okay, so this is nothing but the complementary CDF of assigner, 1 minus CDF of assigner. And you can think of this in the following three ways also. This is the probability that a random chosen user can achieve the target assigner tau, or it's an average fraction of users who at any time achieve this threshold. So basically, if I say that a user randomly chosen see 50% of time this threshold, it means 50% of user will see this threshold. And since the user process is stationary, you can also say the average fraction of the network, which see for which the coverage, which is in the coverage at any time, that is also the coverage probability. Okay, so now we will characterize this assigner for typical cases, and the first scenario we will take is a cell network with fading. And you recall the fading one is the easy one than the no fading case, which would be the case here also. So the system model we're going to take is very similar to the Manet case. We'll take the same power law path model where the receive power at a distance d is proportional to dt power minus alpha, where alpha is the pathless exponent. Base stations are located according to a homogeneous Poisson point process with density lambda in R square space. Xi denotes the location of the ith base station. And also, x0 is the location of the serving base station. Mobile users are as independently located according to some other stationary point process. So we do not assume that it's a PPP, the user process, but just some point process which is stationary. And as I said earlier, all analysis for a typical user, why not at the origin? And this typical means it user selected from 5 user arbitrarily without any special condition. So it truly depicts the average user. So we consider the average received power as the power level. Okay, so this, as you can see, this will be average received power based association because the power level only include the average received power. So this function x would be pt into norm of x minus s. Norm of x is the distance between the base station at x and the user. See, there can be some other factors like near field gain C which are constant, but we can very well incorporate in the noise, right? As you can see, suppose your assigner is signal plus interference plus noise, and signal interference both has a C factor. You can divide that in the assigner expression, and the C factor will be just noise by C. And the assigner would still remain same if we just scale the noise by C. So that is what you can say. If the noise is sigma square, the effective noise you can take is just sigma square by C. So this way you can incorporate any other factors which are constant. So this user will connect to the base station that provides the highest average assigner, which is equivalently the one providing the highest average assigner, or basically it is same as the one being the closest base station. Okay, so since the power level itself is the the power level itself is the average say power, you can see the association function gp is nothing just by the p, because we are going to maximize this gp function. Okay, and since we are maximizing the c power itself, gp is nothing but the p. Okay, so do not get lost in all those notation. You can just simply see that here I am going to check each base station and select the base station who will provide me the highest average receive power. Okay, or which basically means is the closest base station, because the average power, and the average power decreases with x. Okay, so now you have to be careful that we are not incorporating instantaneous receive power or assigner. So it may happen that some base station which is not actually the closest but may experience very good fading and provide the highest instantaneous assigner. But we are not selecting that. We are selecting the base station which provide the average one, average receive power, which is the closest one. Okay. As a fading, we will assume the exponential fast fading. This means it's a Rayleigh fading, but the fading variable is exponentially distributed. This is the same with the Manet case. Okay, so now we come to the instantaneous power. So instantaneous power is nothing but the average power multiplied by the fade. So this HP function, which denotes the instantaneous power, is nothing but H into P. And this H are independent copy denoting fading for each base station, and they are different. Okay, so this means that if you take the ith base station, you will denote this fading by hi, then the instantaneous power of that base station is hi into transmit power into the distance, which is norm xi to power minus alpha. Similarly, the base station which is serving is x naught. So serving power is nothing but PR x naught, which is h0 into pt transmit power into distance to power minus alpha. And the interference, which is the summation of the received power from all the base station except x0, can be written as summation over all xi belongs to phi minus x0. Phi minus this set minus x0 means phi is a set of all base station. You remove x0 from that. This is set minus. And you sum over all those xi, the received power, which is given by hi pt x minus alpha. This is the interference, and we will denote it by I, and just recall that this is a function of x naught and the whole point process phi, because you are adding over all points in the phi. So if you look at the serving power in the SNR expression, it is a function of fading and the distance between the serving base station and the user. User is at the origin and the serving base station is x0. So distance is just the norm of x0, which we also call as r0. Okay, so in the managed case, remember we have serving base station to the user distance was always fixed, but that is not the case here. The user is fixed and the PPP base station can be anywhere, and the user select the closest base station. Now this base station can be the distance to the serving base station can be very small, or it can be large also, because the PPP is a random deployment. So it's the random variable, depends on the realization of PPP. So we need to calculate a distribution to be able to understand what the assigner characterization. So first let's compute the probability that the x0 norm or distance r0 is more than r. So the event that x0 is more than r, it means the closest base station is outside the ball of r. So if the closest base station is outside the ball of r, means all other base stations should be outside the r. Okay, so the probability that the x0 is outside the ball of r, it is equal to the probability that there is no base station in the ball of radius r. And the probability that there is no base station in any area is equal to e to power minus lambda a, the void probability. So probability that there is no base station in the ball of r would be equal to e to power minus lambda into a volume area of the ball, which is pi r square. So it is e to power minus lambda pi r square. So we can say so if you take norm x0 as r0, then we can just say probability that r0, the distance, is more than r is equal to e to power minus lambda pi r square. There is a CCDF. The CDF, the probability that r0 is less than or equal to r, is nothing but 1 minus probability that r0 is more than r, and so it is equal to 1 minus exponential minus lambda pi r square. So from the CDF we can calculate the PDF just by differentiating the CDF with respect to r. So we will just get 2 pi lambda r into exponential lambda pi r square, and r is more than 0, so there is no density in the negative axis. So before we calculate the assigner characterization, let's take a simple case and let's assume SNR. And here we will not assume any fading, just for simplicity. So let's assume the H0 is 1. So SNR is nothing but the received power by sigma n square, which is fading, which is 1 pt into x0 minus alpha, x0 norm minus alpha divided by the noise power. Okay, so the probability, you can calculate probability that SNR is above threshold, which we call the SNR coverage probability, or you can also compute the outage probability, which is probability that SNR is below threshold T, which means system is an outage. So the coverage probability of SNR is equal to probability that SNR is above threshold, which is equal to probability that transmit power into x0 minus alpha divided by sigma n square greater than tau. Okay, so we assume H0 is 1, so there is no fading for now in this case, and there is only one random variable x0, and whose distribution, and also not the whole x0, just the norm of x0, whose distribution we know. Okay, so this is like the probability of this, which is nothing but the expectation of the indicator that H0 pt x0 norm minus alpha divided by sigma square is more than tau. And the expectation is nothing but the integration of that term with respect to distribution of R0. So expectation of indicator would be equal to integration of the indicator with respect to the distribution of R0. So we put the distribution of R0 here, which is 2 pi lambda R0 e to power minus lambda pi R0 square d R0. Now we just take a substitution, lambda pi R0 square equal to T, and you will get that the probability of coverage SNR is equal to integration of indicator that T is less than lambda pi tau sigma n square to the power minus 2 by alpha e to the power minus t dt. Okay, an indicator can be changed and the range over t, which is 0 to lambda pi tau sigma square to the power minus 2 by alpha e minus t dt. This is a very simple integration, and this just gives you 1 minus e to the power minus lambda pi tau sigma square minus 2 by alpha. And outer's probability will be just 1 minus pc if you wish to calculate. So this will be just exponential to this term. Now we can see the outage probability at any typical user decrease exponentially with respect to density. So if you double the density, the outage probability will be half. Okay. Further, in order to maintain the constant outage, increase in the noise power should be accompanied by a densification of the base station. So if you increase sigma n square, you should increase lambda also, so that the both cancels. Okay, and they're not proportional linear relation. You can see if you double the noise, then the lambda should increase by 2 to the power 2 by alpha factor. Okay, so now you can see the importance of the analysis by this simple calculation. Normally what you have to do is, if you want to study what happens when the noise is doubled, you just write a simulation, compute for a particular noise, and then double the noise, and then plot the behavior again, then change different densities and see which lambda the performance is same as the previous one. Okay. The analysis avoids all those things and just give a very simple relation between lambda and the noise and the outage probability, and you can very simply see that if I want to make P0 constant and if I want to double the noise, then what should I do with the lambda? Okay, so this just small example tells you the importance of the analysis. Okay, let's come back to the SINR again. So just recall SINR is nothing but the instantaneous serving power divided by the total instantaneous interference power plus noise. Okay, so serving power we kind of know, the distribution of serving distance we know. Before proceeding, we need to know the distribution of interference. How do we characterize the interference? Okay, there is one crucial difference between this interference and the interference in the manet. Right? Remember, in manet, interference can be anywhere. Right? It can be closer to you than your own serving base station, because the pairing is fixed and your serving base station are distance, but the users are PPP. So sorry, the other transmitters are PPP. So it is possible that there is some other transmitter which is very close to you, even closer than your serving power. Okay. That is why the interference is so high in manet, that we see the mean is always infinite. But that is not the case with the cellular case. Why? Because we selected the serving base station out of all base station as the closest base station. So it means the interfering base station cannot be closer than the serving base station, because if it is, then that base station will be selected as the serving base station. This means if the serving base station is at the distance of R0, then all the base stations are outside this ball. So there is an exclusion ball created around the user and with the distance R0, in which no interferer can exist. So if we condition on the serving base station location, condition on that the interferers can only be outside this exclusion ball. So as discussed, the interference, because of this exclusion ball, all the interference are outside the ball, and the serving power on the average is better than any interfering power. So the interference should be smaller than the manet case, and that should improve the performance. Okay, so how do I characterize this? So as we discussed last time, interference is summation over all xi except x0, and the receive power of all xx. And this does not say this exclusion of base station in this equation, but there is one condition, right? So to explicitly write that, We will just include one indicator which says that we are adding all the base station exercise power with indicator that xi norm should be more than the norm of x naught. It just means that xi should be at a distance further away than the xg. So this extra indicator does not change anything because xi in eventually will be outside x naught also because of the conditioning, but when we write it, the conditioning is very much clear and explicit. Okay, now we know that this term of interference does not include x naught. So if you recall the Sirnac theorem, any function of the PPP where you condition on one point and you do not consider that point is same as the PPP which is unconditional with the same density. So if I take an independent PPP phi naught and define an interference from all points of phi naught in the following way, that I2, which is a function of phi 2, is an x0 also is equal to indicator over all yi's in phi 2 of the received power hi pt into yi distance minus alpha multiplied by indicator that yi greater than x naught. So this form is same as I, but in I2 phi is unconditioned and include all points. In I it is conditioned on the x0 and does not include x0. Both should have the same distribution. It means the distribution of I and I2 should be same, right? So distribution same means the Laplace transform would be same, the mean would be same, every other thing would be same. So let's first calculate the mean of the interference. Okay, and everything I'm conditioned on the serving, I'm conditioning on the location of the serving base station. Okay, and then I'll decondition in the end because I already know the distribution of x0, so I can decondition in that. But right now I am characterizing the interference condition on the location of x0. So mean will be same way also. The mean of interference I is same as the mean of I2. Okay, and I2 is very easy to calculate because there is no conditioning in that. So that is equal to expectation over summation over all yi in phi 2 with this function of yi. Okay, recall in this case x0 is not part of phi 2, right? But because there is a x0 term, the whole thing is of course a function of x0. Now this is a function over this is the function of ya in summation over all points. So we can apply Campbell theorem for the marked Poisson point process, and we get that mean of I2 or the mean of I is equal to lambda into integration of fx dx. Okay, in this case fy dy. And what is the function? Function is nothing but fy here is equal to hi into pt into y norm minus alpha into indicator y norm greater than norm of x naught. Okay, and because it's a Markov process and h0 is fading, the expectation with respect to h0 would also be there. Rest of the function is independent of h0, so the expectation will be only outside h. Now we can convert y to the polar coordinates r theta. In that case, this integration will become lambda pt integration of EH into r minus alpha, then indicator that r, which is the norm of y, r greater than norm of x naught. Then r theta, these are, there will be integration with respect to the theta and r. Now this indicator that r is greater than norm of x naught will just change the limits of r, and the limit will eventually becomes for r as norm of x naught to infinity. The limit of theta would still be 0 to 2. Okay, so theta, there is no function of theta, so you can integrate it very much and just call it 2 pi. And the integration with respect to r would be equal to integration from norm of x naught to infinity r to the power minus alpha r dr. Okay, and this can be simply calculated, and you will see the integration of r minus alpha plus 1 is r minus alpha plus 2 divided by minus alpha plus 2, and then you put limits from norm of x naught, which is r0 to infinity, and that will just becomes 2 pi lambda pi t into r to the power minus alpha plus 2 divided by minus alpha plus 2. Now this function again depends on value of alpha